April 15, 1986. The Mediterranean sky above Libya's coastline stretched endlessly in every direction as Major Brian Schul felt the familiar thrust of the Pratt& Whitney J58 turboramjet engines, pushing his SR-71 Blackbird through the thin atmosphere at 80,000 feet. Schul and his reconnaissance systems officer, Major Walter Watson, had crossed Muammar Gaddafi's self-proclaimed line of death, a disputed maritime boundary that the Libyan dictator swore he would defend with lethal force. Their mission was straightforward but perilous: conduct bomb damage assessment over Tripoli following the previous night's American airstrikes against terrorist training camps. Satellites were not immediately available for real-time imagery, so the SR-71 was dispatched to gather photographic intelligence that would determine whether Operation El Dorado Canyon had successfully neutralized its targets. As Schul banked the aircraft for its final reconnaissance pass, Watson's voice crackled through the intercom with a warning no Blackbird crew ever wanted to hear. Multiple surface-to-air missile launches had been detected. Libyan air defense batteries, equipped with Soviet-made SA-2 Guideline and SA-4 Gonif missiles capable of speeds exceeding Mach 3.5, had begun firing upward toward the American reconnaissance jet. In that instant, Schul did what every SR-71 pilot was trained to do when missiles were inbound. He advanced the throttles beyond the official cruise setting of Mach 3.2, pushing the Blackbird into a regime of flight that exceeded even Lockheed's published performance envelope. The airframe began to heat rapidly, expanding by several inches as aerodynamic friction transformed the titanium skin into a glowing thermal barrier. Fuel temperature spiked as the JP-7 acted as a heat sink for the aircraft's critical systems. The twin J-58 engines, each inhaling 100,000 cubic feet of air per minute, transitioned fully into ramjet mode, with the inlet spikes generating 54% of the total thrust while the engines themselves contributed less than 18%. The afterburners roared at maximum continuous burn, sustaining internal temperatures of 3,200 degrees Fahrenheit, while ceramic thermal barrier coatings kept the ducts from melting. Schul later reported that the aircraft surpassed Mach 3.5 during that egress, a speed so extreme that the Libyan missiles, despite their own hypersonic velocity, simply could not close the distance. The SA-2 and SA-4 missiles exhausted their delta-V during the climb to altitude, and by the time they reached 80,000 feet, they were ballistic projectiles following parabolic arcs with no remaining energy to maneuver. The Blackbird accelerated away, leaving the missiles to tumble uselessly back toward the desert below. Schul and Watson returned to their forward operating base without a scratch, their reconnaissance cameras filled with high-resolution stereo imagery that confirmed the success of the previous night's bombing campaign. It was one of thousands of such missions flown by the SR-71 during its 25-year operational career, and it encapsulated the aircraft's singular defensive philosophy. Speed was not merely an advantage, it was an absolute shield. The Soviets had mocked the SR-71 from the moment American President Lyndon B. Johnson revealed its existence in July 1964. During the height of the Cold War, Soviet military leadership viewed the Blackbird as yet another expression of American technological arrogance, a reconnaissance platform that relied on speed and altitude rather than true stealth or defensive countermeasures. Soviet Air Defense Forces, known as the PVO Strany, considered the SR-71 a tractable problem. Their radar networks stretched across the entire Warsaw Pact frontier, from the Baltic Sea to the Black Sea, forming an integrated air defense system that could detect, track, and engage high-altitude intruders with overlapping coverage. Soviet doctrine emphasized redundancy and saturation. If one missile battery failed to intercept an American reconnaissance jet, 3 more would be positioned along its flight path to ensure destruction. Soviet engineers believed that no aircraft, regardless of speed or altitude, could evade a coordinated missile barrage supported by real-time radar tracking and ground-controlled interception. The Mikoyan-Gurevich Design Bureau had already developed the MiG-25 Foxbat, an interceptor capable of sustained speeds above Mach 2.8 and brief sprints beyond Mach 3.2 at altitudes exceeding 80,000 feet. Soviet leadership publicly stated that the MiG-25 was specifically engineered to counter high-speed American reconnaissance platforms. Internal Soviet reports from the late 1960s expressed confidence that the Foxbat could achieve a favorable intercept geometry against the SR-71, particularly if Soviet radar stations provided precise targeting data, and the MiG-25 pilot executed a head-on attack profile with R-40 air-to-air missiles. Soviet surface-to-air missile systems were equally formidable. The SA-2 guideline, which had successfully shot down Francis Gary Powers' U-2 spy plane over Sverdlovsk in May 1960, remained in widespread deployment across the Soviet Union and its client states. The SA-2 had a maximum speed of Mach 3.5 and a ceiling of 60,000 feet, sufficient to engage high-altitude bombers and reconnaissance aircraft. The SA-5 Gammon, introduced in the mid-1960s, extended Soviet air defense reach even further, with an operational ceiling above 90,000 feet and a range exceeding 200 miles. Soviet military journals openly discussed the SR-71's vulnerabilities, noting that while the aircraft possessed impressive speed, it lacked active defensive countermeasures such as chaff dispensers, flare launchers, or onboard jamming pods capable of disrupting missile guidance radars. Soviet analysts calculated that the SR-71's small radar cross-section, estimated at approximately 110 square feet, would provide only marginal protection. Once detected, the Blackbird would remain visible on Soviet radar screens long enough for missile batteries to calculate intercept solutions and launch salvos. Soviet air defense commanders believed that even if the SR-71 could outrun a single missile, it could not outrun a coordinated volley of 10 or 20 missiles fired from staggered positions along its flight corridor. This confidence extended to the highest levels of Soviet military command. Marshal Pavel Batitsky, commander-in-chief of the Soviet Air Defense Forces during the 1960s, reportedly stated that American reconnaissance overflights were a temporary nuisance that Soviet technology would soon render obsolete. Soviet propaganda outlets described the SR-71 as a symbol of American desperation, a costly and fragile platform that demonstrated Washington's inability to develop true satellite reconnaissance capabilities. Soviet military planners expected that within a few years, improved radar systems, faster interceptors, and more sophisticated missile guidance algorithms would close the performance gap, rendering the Blackbird as vulnerable as the U-2 had been in 1960. Yet no one expected what would happen next. The SR-71 Blackbird was not merely fast. It was a product of Lockheed's Skunk Works division, an elite engineering team led by Clarence Kelly Johnson, whose previous designs included the P-38 Lightning, the F-80 Shooting Star, the F-104 Starfighter, and the U-2 Dragon Lady. Johnson understood that speed alone would not guarantee survival against Soviet air defenses. The SR-71 required a combination of velocity, altitude, reduced radar signature, and aerodynamic efficiency that pushed the boundaries of materials science, propulsion technology, and structural engineering. Development of the SR-71 began in the late 1950s under the codename Project Oxguard, initially focused on the A-12 reconnaissance aircraft for the Central Intelligence Agency. The A-12 first flew at Area 51 in April 1962, achieving speeds above Mach 3.2 and operational altitudes exceeding 85,000 feet. The SR-71, derived from the A-12 but lengthened to accommodate a two-person crew and additional fuel capacity, incorporated every lesson learned from the A-12 program. The Blackbird's airframe was constructed from titanium alloy, a material chosen for its exceptional strength-to-weight ratio and ability to withstand sustained temperatures exceeding 600 degrees Fahrenheit. Titanium comprised 85% of the SR-71's structure, with the remainder consisting of polymer composites and specialized alloys. Lockheed's engineers faced unprecedented challenges working with titanium. The metal required distilled water for welding, as chlorine in tap water caused corrosion. Cadmium-plated tools could not be used as they also induced corrosion. At one point, 80% of the titanium delivered to Lockheed's Burbank facility was rejected due to metallurgical contamination. The Soviet Union was the world's leading supplier of titanium during the 1960s, and the Central Intelligence Agency established a network of shell companies to covertly purchase Soviet titanium for use in constructing an aircraft specifically designed to spy on the Soviet Union itself. The irony was not lost on American intelligence officials, who later acknowledged that Soviet titanium formed the structural backbone of the very platform Moscow sought to destroy. The titanium procurement operation represented one of the most audacious intelligence coups of the Cold War. The United States required rutile ore, a sandy titanium-bearing mineral found in only a few locations worldwide, with the Soviet Union controlling the largest deposits. Working through Third World intermediaries and establishing bogus mining companies across multiple continents, American intelligence officers purchased thousands of tons of Soviet titanium without arousing suspicion in Moscow. The ore was shipped through circuitous routes, often passing through 3 or 4 countries before reaching American refineries. Soviet export officials believed they were selling raw materials for commercial applications such as chemical processing equipment and marine hardware, never suspecting that their titanium would form the skeleton of America's most advanced reconnaissance aircraft. Colonel Rich Graham, a former SR-71 pilot and wing commander, later revealed that the aircraft was 92% titanium by weight, with virtually every structural component dependent on Soviet-supplied material. The machining process itself proved extraordinarily difficult. Early drill bits used to create rivet holes in titanium panels could only complete 17 holes before becoming unusable and requiring disposal. Lockheed engineers spent years developing specialized cutting tools, coolant systems, and machining techniques that could handle titanium's unique properties. By the end of the SR-71 program, advanced drill bits could complete 100 holes before requiring sharpening, and manufacturing costs had been reduced by $19 million through cumulative process improvements. Titanium's sensitivity to heat, its tendency to work harden during machining, and its brittle fracture characteristics when dropped or improperly handled forced Lockheed to retrain its entire workforce. Conventional metalworking techniques developed for aluminum and steel were useless when applied to titanium. Workers had to learn that titanium required slower cutting speeds, higher volumes of coolant, and deeper cuts per pass to prevent work hardening of the surface layer. The material's low stiffness caused it to deflect during machining, creating dimensional inaccuracies that required constant adjustment. Lockheed machinists discovered through painful trial and error that summer-manufactured titanium parts corroded at accelerated rates, while winter-manufactured parts remained stable. The explanation was eventually traced to chlorine levels in Burbank's municipal water supply. During summer months, higher chlorine concentrations were used for purification, and trace amounts remained on workers' hands, contaminating titanium components during assembly. This discovery led to mandatory use of distilled water for all cleaning operations and the implementation of strict contamination control protocols throughout the manufacturing facility. The SR-71's propulsion system represented a revolutionary hybrid design. Each Pratt & Whitney J58 engine functioned as an afterburning turbojet during takeoff and transonic acceleration, then transitioned into a low-bypass turbofan during supersonic climb, and finally operated as a turboramjet during sustained Mach 3 cruise. At maximum velocity, the engine itself contributed only 17.6% of total thrust. The inlet system, featuring a movable spike that adjusted position based on airspeed and altitude, generated 54% of thrust through ram pressure compression. The ejector nozzle, which mixed primary engine exhaust with secondary bypass air and tertiary blow-indoor air, contributed the remaining 28.4%. This distribution of thrust was radically different from conventional jet engines, where the turbine and combustor provided nearly all propulsive force. The SR-71's inlet spikes moved automatically to maintain optimal shockwave positioning, ensuring that supersonic airflow was efficiently compressed and decelerated to subsonic speeds before entering the engine compressor. If the inlet shock wave destabilized and moved forward past the cowl lip, an unstart occurred, causing a sudden loss of engine power and violent yawing motion that could disorient the crew and destabilize the aircraft. Early SR-71 flights experienced frequent unstarts, with analog control systems unable to respond quickly enough to prevent shock wave displacement. Lockheed engineers eventually developed a digital automatic flight and inlet control system, known as DAFICS, which reduced unstart incidents by continuously monitoring inlet pressure ratios and adjusting spike position in milliseconds. The J-58 engines consumed JP-7 fuel, a specialized low-volatility kerosene with an extremely high flash point that made it nearly impossible to ignite under normal conditions. To initiate combustion during engine start, the SR-71 used trithylborane, a pyrophoric chemical that ignited spontaneously upon contact with air, producing a distinctive green flame visible during ground operations. The JP-7 fuel also served as a coolant for the aircraft's hydraulic systems, environmental control systems, and cockpit air conditioning, absorbing waste heat before being burned in the engines. The SR-71's fuel tanks were integral to the airframe, with the outer skin forming the tank walls. Because titanium expands significantly when heated, the fuel tanks were deliberately designed with loose panel fits on the ground, allowing thermal expansion during flight to seal the gaps. As a result, the SR-71 leaked fuel while parked, leaving trails of JP-7 on the tarmac. This was not a design flaw but an intentional feature. The aircraft was assembled cold and sealed hot, with the airframe reaching its final structural integrity only at sustained Mach 3 cruise, when aerodynamic heating expanded the titanium skin by up to 6 inches. The SR-71's shape was equally critical to its survivability. Lockheed's engineers incorporated chines, sharp leading edges that extended aft from the nose along the fuselage, creating a flattened cross-section that deflected radar energy away from the transmitter. The vertical stabilizers were canted inward to reduce radar reflections, and the aircraft's surfaces featured sawtooth patterns embedded with radar-absorbent materials. These design elements reduced the SR-71's radar cross-section to approximately 110 square feet, far smaller than its physical dimensions would suggest. For comparison, a Boeing 747 has a radar cross-section exceeding 1,000 square feet, while a fighter jet like the F-15 Eagle has a cross-section of approximately 100 square feet. The SR-71's reduced signature meant that Soviet radar operators would detect the Blackbird later and track it for a shorter duration than conventional aircraft, compressing the window of opportunity for launching interceptors or missiles. The chines also generated powerful vortices along the fuselage, creating additional lift and allowing the wings to operate at lower angles of attack. This improved fuel efficiency, increased range, and reduced structural stress during high-speed flight. The chine's aerodynamic benefits were discovered accidentally during wind tunnel testing and became one of the SR-71's most distinctive features. The Blackbird's operational profile exploited fundamental limitations in Soviet air defense architecture. Surface-to-air missiles like the SA-2 and SA-5 required several minutes to calculate firing solutions, position launch rails, and execute launches. By the time Soviet radar operators detected an SR-71, identified it as a high-priority target, and authorized a missile launch, the Blackbird had already traveled dozens of miles. The missiles themselves faced insurmountable physics. Climbing from sea level to 85,000 feet consumed nearly all of a missile's kinetic energy. Even if an SA-2 reached the SR-71's altitude, it would be traveling at a fraction of its initial velocity, with minimal remaining energy for maneuvering. The SR-71, meanwhile, maintained Mach 3.2 or higher, creating a closing speed problem that no Soviet missile guidance system could solve. If the Blackbird detected a missile launch, the pilot's response was not evasive maneuvering but acceleration. Simply advancing the throttles was sufficient to outrun the threat. Soviet interceptors faced similar challenges. The MiG-25 Foxbat was fast, but it could not sustain Mach 3 for extended periods without catastrophic engine damage. Soviet pilots were prohibited from exceeding Mach 2.8 during routine intercepts to preserve engine life. The MiG-25's operational ceiling was approximately 80,000 feet, roughly equivalent to the SR-71's cruise altitude, but the Foxbat's climb rate and acceleration were inferior to the Blackbird's sustained performance. Soviet intercept doctrine relied on ground-controlled radar stations directing MiG-25 pilots toward predicted intercept points. Swedish radar operators monitoring Baltic Sea overflights observed Soviet MiG-25s attempting to close on SR-71 reconnaissance missions during the 1970s and 80s. Swedish intelligence reports noted that Soviet Foxbats would typically approach to within 1.9 miles of the SR-71, positioning themselves at approximately 62,000 feet, while the Blackbird cruised at 72,000 feet. The Soviets interpreted this as a successful simulated shootdown, demonstrating that the MiG-25 could achieve a favorable firing position under ideal conditions. Swedish Air Force pilots flying Saab 37 Viggen interceptors also attempted to lock onto SR-71s, transiting international airspace between the Swedish islands of Åland and Gotland. The Viggen's advanced radar system, combined with precise targeting data from ground-based radar stations, allowed Swedish pilots to achieve missile lock on 51 occasions out of 322 recorded SR-71 sorties between 1977 and 1988. However, Swedish pilots acknowledged that successful engagement required the SR-71 to maintain a predictable flight path and constant velocity. Any deviation in the Blackbird's speed, altitude, or heading would break the radar lock and render the intercept impossible. The Viggen's maximum speed of Mach 2.1 and service ceiling of 59,000 feet meant that Swedish pilots had to rely on perfect timing and advanced knowledge of the SR-71's route. Soviet pilots faced identical limitations, with the added challenge that American reconnaissance missions over Soviet territory were rare and unpredictable. The SR-71 flew reconnaissance missions that redefined intelligence collection across multiple theaters. During the Vietnam War, Blackbirds operated from Kadena Air Base in Okinawa under the codename Giant Scale, conducting overflights of North Vietnam and Laos that monitored surface-to-air missile deployments, tracked enemy troop movements, and provided bomb damage assessment following American airstrikes. North Vietnamese air defense forces fired dozens of SA-2 missiles at SR-71s throughout the conflict, but none achieved a successful intercept. The Blackbird's speed and altitude rendered it effectively invulnerable, allowing American commanders to gather intelligence without risking pilot lives or aircraft losses. Missions along the Soviet Union's Baltic and Barents Sea coastlines, flown from RAF Mildenhall in the United Kingdom, mapped Soviet naval facilities, tracked submarine deployments, and monitored air defense radar networks. Soviet forces launched hundreds of missiles at SR-71s during these missions, but the results were identical. No Blackbird was ever hit. Over Cuba, the SR-71 conducted reconnaissance missions to verify Soviet military activities following the Cuban Missile Crisis, ensuring that nuclear-capable weapons systems were not reintroduced to the island. Declassified Central Intelligence Agency documents confirm that SR-71 overflights of Cuba originated from Beale Air Force Base in California, with aerial refueling tankers providing mid-mission fuel transfer to extend the Blackbird's range. These missions delivered photographic and electronic intelligence that shaped American policy toward the Castro regime and provided early warning of Soviet attempts to re-establish a military presence in the Western Hemisphere. Over the Korean Peninsula, SR-71 missions monitored North Korean military installations, tracked troop concentrations along the demilitarized zone, and gathered signals intelligence on North Korean radar and communication networks. On August 25, 1981, North Korea launched an SA-2 missile at an SR-71 flown by pilot Maury Rosenberg and Reconnaissance Systems Officer Ed McKim during a reconnaissance pass along the demilitarized zone. The missile missed by several miles, but the incident infuriated President Ronald Reagan, who personally demanded a forceful response. 10 days later, Assistant Secretary of Defense Frank Carlucci visited the SR-71 detachment at Kadena Air Base and briefed crews on a revised operational plan. American reconnaissance missions were temporarily adjusted to fly 30 miles south of their normal flight paths, but within weeks, the decision was made to resume normal operations. On October 26, 1981, SR-71 pilot Jay Reed and Reconnaissance Systems Officer flew a mission identical to the one during which North Korea had fired, deliberately overflying the missile launch site within 10 seconds of the precisely calculated time. American intelligence agencies had positioned F-4 Phantom fighter bombers armed with air-to-ground missiles on high alert, ready to strike the North Korean missile battery if a second launch was detected. The North Koreans did not fire, and the message was clear. The United States would not be deterred. The SR-71's reconnaissance systems transformed raw speed into actionable intelligence. The aircraft carried optical cameras, infrared sensors, side-looking airborne radar, and electronic intelligence gathering equipment capable of mapping enemy radar networks, intercepting communications, and identifying air defense installations from altitudes above 80,000 feet. The IDEC optical bar camera provided continuous horizon-to-horizon coverage, capturing stereo imagery with resolution sufficient to identify individual vehicles and structures. The HYCON technical objective camera could be directed up to 45 degrees left or right of the flight center line, allowing the reconnaissance systems officer to target specific areas of interest. Advanced synthetic aperture radar systems, such as the ASARS-1 developed by Loral, generated high-resolution ground maps regardless of weather conditions or time of day. Electronic intelligence sensors built by AIL analyzed radar emissions, communication signals, and electronic warfare systems, building comprehensive profiles of Soviet air defense networks. Every SR-71 mission generated thousands of images and hours of signals intelligence data, which were analyzed by National Reconnaissance Office specialists and distributed to military commanders, intelligence analysts, and policymakers. The Blackbird's ability to overfly denied territory with impunity provided the United States with strategic intelligence that shaped Cold War military planning, arms control negotiations, and crisis management decisions. If you appreciate discovering Cold War secrets hidden for decades, consider subscribing for future declassified revelations. Declassified Soviet military reports from the 1980s reveal the depth of Moscow's frustration with the SR-71 program. A Soviet air defense forces analysis obtained by Western intelligence agencies after the Cold War concluded that intercepting an SR-71 Blackbird required perfect coordination of radar tracking, missile launch timing, and aircraft trajectory prediction, and that even under optimal conditions, the probability of a successful engagement was unacceptably low. The report acknowledged that Soviet air defense networks could detect and track the SR-71, but that the aircraft's speed created a temporal window of vulnerability lasting less than 90 seconds, insufficient for effective missile guidance and terminal intercept. Soviet engineers proposed several countermeasures, including the development of faster surface-to-air missiles, improved radar tracking algorithms, and deployment of the MiG-31 Foxhound interceptor, which featured a more powerful radar system and longer-range R-33 air-to-air missiles. The MiG-31 entered service in 1981 and was specifically designed to counter high-speed reconnaissance platforms. Soviet claims that the MiG-31 successfully deterred SR-71 overflights were partially accurate, but the deterrence was strategic rather than tactical. By the early 1980s, American satellite reconnaissance capabilities had matured to the point where the SR-71 was no longer required to overfly Soviet territory directly. The KH-11 Kennan electro-optical reconnaissance satellite, operational since December 1976, provided near real-time imagery with resolution comparable to the SR-71's cameras. American reconnaissance strategy shifted toward peripheral missions along Soviet borders, where the Blackbird sensors could collect intelligence from international airspace without violating Soviet sovereignty. This operational adjustment reduced the political risk of overflights while maintaining intelligence collection effectiveness. The SR-71's defensive systems complemented its speed and altitude. The aircraft carried multiple electronic countermeasures suites, designated systems A, A2, A2C, B, C, C2, E, G, H, and M, each tailored to counter specific Soviet radar frequencies and missile guidance systems. These systems included radar warning receivers that alerted the crew to missile launches, active jammers that disrupted radar tracking, and chaff dispensers that created false radar returns. Major Jerry Crew, a reconnaissance systems officer who flew numerous SR-71 missions during the 1980s, described his use of electronic countermeasures during a mission over hostile territory. When his threat warning receiver indicated a missile launch, Crew activated jamming systems to confuse Soviet radar operators and degrade missile guidance accuracy. Once the missile was airborne and tracking the SR-71, Crew switched off the jammer to prevent the missile from homing in on the electronic signal. Instead, the crew relied on the Blackbird's speed to outrun the threat. This tactic proved effective on thousands of occasions, reinforcing the fundamental principle that speed was the SR-71's primary defense. The aircraft's titanium skin, although not designed for stealth, absorbed and radiated infrared energy efficiently, reducing the Blackbird's thermal signature and complicating infrared missile guidance. The SR-71's exhaust plumes remained highly visible, but cesium-based fuel additives reduced radar reflectivity of the engine exhaust, providing marginal additional protection against radar-guided missiles. The SR-71's operational record is unparalleled in military aviation history. Between 1966 and 1990, the Blackbird flew more than 3,500 reconnaissance missions over 25 years, covering hostile territory in Southeast Asia, Eastern Europe, the Middle East, North Africa, and the Korean Peninsula. During that time, over 4,000 surface-to-air missiles were launched at SR-71 aircraft. Not a single Blackbird was lost to enemy action. 12 of the 32 SR-71s built were lost in accidents, primarily due to mechanical failures, pilot error, or unstarts during high-speed flight, but none were shot down by enemy fire. The closest any SR-71 came to destruction occurred during the Vietnam War, when a Blackbird narrowly evaded two North Vietnamese SA-2 missiles that detonated close enough to cause visible shock waves but inflicted no damage. The SR-71's perfect combat record stands in stark contrast to other American reconnaissance platforms. The U-2 Dragon Lady, despite its high-altitude capabilities, was vulnerable to surface-to-air missiles, as demonstrated by Francis Gary Powers' shootdown in 1960 and subsequent losses over Cuba and China. The Lockheed A-12, the SR-71's CIA predecessor, lost one aircraft during a training accident but never suffered combat losses during its limited operational deployment. The SR-71's invulnerability was not accidental. It was the result of meticulous engineering, rigorous pilot training, disciplined operational procedures, and an unwavering commitment to speed as the ultimate defensive strategy. Soviet military leadership eventually abandoned efforts to intercept the SR-71 through conventional means. Internal Soviet documents from the mid-1980s acknowledged that the costs of attempting to counter American high-speed reconnaissance platforms exceed the strategic value of preventing isolated intelligence collection missions. Soviet resources were redirected towards satellite anti-satellite weapons, electronic warfare, and deception operations designed to mislead American reconnaissance, rather than physically destroy reconnaissance platforms. The SR-71 had fundamentally altered Soviet air defense doctrine, forcing Moscow to accept that certain American capabilities could not be countered through traditional interception methods. The psychological impact on Soviet military planners was profound. For decades, Soviet air defense doctrine emphasized layered redundancy, with multiple overlapping systems ensuring that no enemy aircraft could penetrate Soviet airspace undetected or unengaged. The SR-71 shattered that assumption. Despite possessing one of the most extensive air defense networks in the world, the Soviet Union could not stop a single American reconnaissance jet from collecting intelligence along its borders. Soviet pilots, radar operators, and missile crews watched helplessly as Blackbirds appeared on radar screens, accelerated beyond intercept range, and vanished before effective countermeasures could be deployed. This sense of technological inferiority extended beyond the SR-71 itself. American advances in stealth technology, precision-guided munitions, satellite reconnaissance, and electronic warfare convinced Soviet leaders that the United States had achieved a qualitative military advantage that could not be overcome through quantitative production alone. The SR-71 became a symbol of American technological dominance, a reminder that superior engineering and innovative design could neutralize numerical superiority and strategic depth. The SR-71 program officially ended in 1990, when the United States Air Force retired the Blackbird fleet due to budget constraints and the maturation of satellite reconnaissance systems. Several aircraft were briefly reactivated in the mid-1990s before final retirement in 1998. NASA operated two SR-71s as research platforms until 1999, conducting aerodynamic studies and testing advanced propulsion concepts. The Blackbird's retirement marked the end of an era in aerial reconnaissance, but its legacy endures. As of 2025, the SR-71 still holds the world speed record for a manned, air-breathing aircraft, having achieved a speed of 2,193.16 miles per hour during a flight from Los Angeles to Washington in 1990. It remains the fastest operational jet aircraft ever built, a testament to Lockheed's engineering brilliance and Kelly Johnson's visionary leadership. Modern reconnaissance relies on unmanned aerial vehicles and advanced satellites, but no platform has matched the SR-71's combination of speed, altitude, range, and survivability. Efforts to develop a successor, such as Lockheed Martin's proposed SR-72 hypersonic reconnaissance aircraft, acknowledge the enduring value of speed as a defensive attribute. Hypersonic vehicles capable of Mach 5 or greater could theoretically outpace even the most advanced surface-to-air missiles, extending the Blackbird's operational philosophy into the 21st century. The SR-71 Blackbird proved that speed was not merely a performance characteristic, but a strategic weapon. In a conflict where knowledge meant survival and intelligence determined victory, the United States built a reconnaissance platform so fast, so high, and so unstoppable that the Soviet Union abandoned the idea of intercepting it entirely. Soviet commanders who once mocked American technological arrogance learned the terrifying truth. Even if every interceptor aircraft and every surface-to-air missile on the Eastern Front fired simultaneously, they could never catch a single Blackbird. The SR-71 revealed that the United States could see everything, and the Soviets could do nothing to stop it. Join us here at Classified Warfare as we uncover the operations and technologies that kept the world on the brink.